Okay, so we're going to talk today about prediction in the world of causal explanation. And as a background, we're going to start by first just describing the differences between explaining and predicting. And there's also a third kind called describing, which I'll mention briefly. And based on that this part is kind of based on the paper To Explain or to Predict, 2010. And then the other paper that we're going to build on top of this is the MISQ 2011 paper, Predictive Analytics in Information Systems Research, Shmueli and Copius, which you read here. Okay. And after that, I'm going to move at the very end of it and describe to you a little bit more how prediction is being used in the most recent years. So I'll show you a few very recent papers in the last 2-3 years so that you get a feel of how these prediction has really shifted a lot. Okay, so I'm going to talk about, again, definitions. That's very important to start with so that we make sure we're using the same terms. And then I'll talk a little bit about how in research, certain kinds of analysis were really taking over monopolies, and in practice, in industry, was kind of other ones. And then I'll show you how explanatory modeling, predictive modeling, descriptive modeling, they're different. And I'll also show you how explanatory evaluation performance is different from predictive performance and different from descriptive performance. So this might also put a lot of pieces that you've heard in other courses together. It's kind of nice. You'll figure out, oh, this is why we're doing things this way or the other. Okay, so I'll show you why they're different. I'll show you a glimpse of how the modeling paths are different. If you're doing this or that, how you would do things differently. And then I'll also show you, I'll talk about how to measure the different performance power. The last part, as I mentioned, is since everything is different and things were really monopolized by certain approaches, which we'll see soon, how did things change? Where are things going next? So I'll talk a little bit about how predictive analytics can be used for causal research, and specifically how things moved forward. All right, so explaining, we have two things. When we're using the word explain, we mean here causal explanations. So in explanatory modeling, we're talking about some kind of a theory, causal theory behind the scenes, psychology, sociology, physics, choose your favorite causal theory. And then we're using a statistical model to test the causal hypothesis, okay? So the hypotheses are stated as causal. We can draw DAGs, right? Causal diagrams. That's explanatory modeling. The other concept here, explanatory power, means that when we are testing these kinds of explanatory theories, we're using the statistical model and measuring the strength of the relationship in this statistical model. Okay, so these are two important terms where we're using the word explanatory. In contrast, when we say predict, then a predictive model or predictive modeling means we're using some kind of an empirical method. So it could be a statistical model, but it can also be a machine learning algorithm, okay, for predicting new observations. Very, very different than what we were trying to do before, right? We care about new observations and we're open to all kinds of empirical methods. The other term here is when we want to talk about performance, we're talking about predictive power, and the predictive power of a predictive model or of any model can even be a predictive power of causal model, right? I can have an explanatory model and I want to assess its predictive power. Then that's the ability of this model to accurately predict new observations. Okay, so these are also different. There's also the third piece, which is description. And description is different from both of them. So a descriptive model or descriptive modeling, the process of modeling in a descriptive way, is again using statistical models. So it's kind of like causal modeling, but there's no causal story going on. There might be a correlation that you're looking at, some relationship that you're looking at, but there are no arrows directing in any way. So when you go to a statistics 101 course, usually they will not use the word causal anywhere, even when they're teaching regression, because they're doing descriptive modeling. Even when you just fit a histogram to the data, that's descriptive modeling, right? You're just looking, what's the distribution? You're not coming up with any causal claims. Okay, what is descriptive power? Again, you can have independent variables and a dependent variable. You can have a regression model, but you're not talking about causal stuff. You just want to see how well this regression model fits the data. So goodness of fit measures, looking at residuals, things like that, that is all part of descriptive modeling. Here, also what we care about is that this model that you find generalizes to the population. So if I fit a regression model for, I don't know, the relationship between how much money you make today and how much money your family will be making in the future, maybe it's just a correlation that I care about, but I want to make sure that whatever I learned from my sample, the betas in the regression, that is going to generalize to a larger population. So that's where statistical generalization really matters. So we're still doing statistical tests and p-values and all that stuff here also, because we're trying to generalize this relationship from a sample to a population. Okay, so in causal modeling, we're also generalizing. In prediction, we're generalizing in a slightly different way. So we're going to talk about those things. Okay, what's interesting is that different fields really kind of monopolize or mostly do one of these kinds of things. So if you think about management science and social sciences, which one of these is most common there? From what we've seen everywhere, they mostly do causal modeling, right? If you look at the field of machine learning, what they typically do, what they care about is really predictive stuff. And the interesting part is the world of statistics, the whole field of statistics, they really care mostly about descriptive modeling, which is not really serving the management and social sciences very much and not very serving the predictive world. Things have changed. There's some groups in statistics that do more predictive stuff, but the most major statistics journals and papers that you'll read about are really about descriptive modeling. Okay, so we kind of have these three kinds of, not talking to each other, and that creates all kinds of interesting opportunities. And explanatory stuff that happens very much in social sciences and management research, right? Very much dominated by this. So for audiences that don't know what explain is, so sometimes I give this talk to an audience of machine learning people or to statisticians, and they don't know what I mean by explain. So I tell them, okay, in a nutshell, right? Here's what it means. So the purpose of explanatory modeling is we want to test some causal theory, and we're going to be using some statistical model that is based on associations, something like a regression model. And that's when statisticians will start perking up and saying, what? A regression model for testing causal theories? That doesn't sound good. That's the knee-jerk reaction of statisticians. But I tell them this is how it's done. And then once you estimate these models, you'll get some results. You're not going to see any prediction. You're not going to see any descriptive stuff. That's not of interest to people who are doing causal explanatory stuff. And here's an example of what it would look like. And I show a picture of something that you probably have seen before, right? These kinds of path models where we start with a causal theory that we might even draw with arrows, where we have constructs leading to other constructs, meaning that one causes the other one. And the idea of having hypotheses on constructs, again, that's very foreign outside of the social sciences and management sciences. Nobody knows what constructs are. The word I didn't even know what a construct was until I started having colleagues outside of statistics. And then we operationalize the constructs and create measurable variables. And then we take these measurable variables and use it to fit some statistical model, right? And finally, we use this statistical model for statistical inference and come up with causal conclusions. So it's kind of interesting because the whole machinery in the middle is not causal. The statistical models are not causal. And everything relies on the causal theory at the beginning. So that's the interesting part. So when you talk to people in classic social sciences or management sciences who not really interested in prediction and description, they will often tell you that, yeah, we build this great model. It explains really well. And the same model that's best for explanation is also great for describing, predicting. So what's your problem? Why are you telling me it's different? And I had colleagues who would tell me something like, a good explanatory model will also predict well. And they were very sure that's true. I had long conversations with colleagues early on. Or other people tell me you can't predict well because you have to understand the underlying causes in order to generate good predictions. So that's the first misconception of people who just come from this world of causal explanation. And they think that if they can explain well, it automatically predicts well. And that's why you'll see people using the R-square from their models and saying, oh, this model has very high predictive accuracy. It's like you haven't done anything predictive, right? Okay. And you can see this in different articles. So here's just a little example from MIS Quarterly, Understanding and Predicting Electronic Commerce Adoption. So this paper here, their goal is to examine the predictive power of a proposed model. We compare it to 4 models in terms of R-square adjusted. Now, granted, these are very early papers, 2006. There was a lot of confusion in this field. So they want to do predictive power, but looking at R-square adjusted. Here's another one, Health Psychology Review. How well does the theory of planned behavior predict alcohol consumption? There is nothing predictive in this paper. Everything here is just a causal explanatory with p-values, testing theories. Here's another one in the Journal of Applied Social Psychology, Predicting and Explaining Intentions and Behavior. How well are we doing? Again, there's nothing predictive inside this paper. If you look at it, no predictions really whatsoever. So there's a confusion here. People think that they're doing prediction, but they're not really doing prediction. Okay, and again, these are papers from, early 2000s or even somewhat later 2000s, depending on which field you're looking at. You can see that in psychology, things even most recently are confused. In IS, things are getting much better. Another misconception that comes from the other community is that they think that if they build a predictive model, it predicts so well, then it explains what's going on. So if you talk to people in computer science or engineering or in statistics, they'll tell you, yeah, just build a really good predictive model and then you can explain what's going on. So here's an example, papers from conferences, because computer science people publish in conferences, right? User exercise pattern prediction through mobile sensing. So in this paper, they say, in this work, we present insights about user exercise patterns by analyzing historical data, and look at what they have in the bullets. Our contribution is summarized. Insights about users' exercise patterns, influential factors. We analyze important factors. That sounds very causal explanatory, right? Prediction. We propose a modeling approach to predict the tendency of users to future number of exercises. Now notice that this is a prediction paper. They actually did predictive stuff in here. But from their model, the model that they're using to predict, they're saying, oh, we found influential factors, factors that make you understand users' exercise patterns. From a predictive model, it's very hard to understand why these factors are not causal. Okay, these are just predictors that are able to predict things. Here's another example on a framework for prediction and explanation of changing opinions. So they're building an agent-based modeling that's a very predictive kind of approach. And they say our model is able to provide both predictions of how the population may vote and why they're voting this way. But actually, this model has no causal stuff in there at all. So the fact that you're able to build a descriptive model or a predictive model doesn't mean that you can actually extract anything causal from it. Nothing, right? There's no theory. And you might notice something interesting here. Here's another very confused paper called Explaining and Forecasting Online Auction Prices and Their Dynamics. And if you look at the list of authors, surprise, I'm in there too. And this was published in 2008 in the Journal of Business and Economic Statistics. And in fact, this paper had a different name. It was called Forecasting Online Auctions. But the reviewers insisted that we should call it Explaining and Forecasting. Although all we did was looking at the different forecasting models and saying, look, this model, we can see that this contributes, that contributes. There was nothing causal in those models at all. So there was a lot of confusion, and I have to carry this badge of honor with me until today. Okay, and here's another one, Wall Street Journal. So this is even when you read the newspapers and you're looking at what companies are doing. So the workforce analytics, using workforce analytics to predict employee turnover. So now there's a lot of software that does prediction of turnover, who's going to leave your company, right? So that the companies can do something about it. I don't know if they fire these people or they just give them more money to keep them. But look at how these software vendors, what they're telling people. They're saying predictive workforce analytics software can help CIOs reduce voluntary turnover by identifying employees in critical roles who may be at high risk for leaving. Blah, 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 blah. They tell you what they're using. They use information about the salary, size and date of their raise, results of recent performance reviews, tenure, vacation time they've taken, everything that's in the logs, right, of the system that you can have about the employee. And finally, they say that this software that they will sell you also highlights the top factors influencing employees' interest in leaving. Now, clearly, if you're just grabbing these variables from the logs, you don't really understand the reasons that are, maybe their spouse is moving to a different city and they have to join them, right? So there's no way that this is explanatory, but yet predictive software is many times now being misrepresented as also providing causal reasons. Okay, there's another kind of misconception that doesn't just confuse things, but actually says one is more important than the other. So in academia, people will sometimes say explaining is a lot more important than prediction, because explaining means we're understanding the world. This is scientific knowledge. Prediction is just for industry. It's just for making some money. There was a very famous statistician by the name of Emmanuel Parzan, who passed away a few years ago. And there's a super famous paper called Statistical Modeling, the Two Cultures, that was written by Leo Breiman in Statistical Sciences. And that paper was the first paper to start saying why statisticians and machine learning people were doing things differently, because machine learners were trying to predict, and the statistics is really geared towards descriptive modeling and statistical testing. And Emmanuel Parzan was one of the commentators on this paper. And in that comment, he writes, the two goals in analyzing data, which Leo calls prediction and information, I prefer to describe as management and science. Management seeks profit, practical answers useful for decision-making in the short run. Science seeks truth, fundamental knowledge about nature, which provides understanding and control in the long run. So when I read this and I was writing the Explain or Predict paper, I sent him an email and I said to him, wait, so do you mean that explaining is science and prediction is management? And he wrote back, and I still have the email, and he said, yes, that's what I mean. So for him, explaining is a lot more important, and prediction is just for making money. It's not really useful for scientific development, which is what I disagree with, right? And that's what we had in the paper. On the other hand, you have people like, I don't know if you've heard the name Chris Anderson, who was the editor of the very well-known magazine called Wired. And when was this from? Oh, goodness, 2008. He wrote this article called The End of Theory. The data deluge makes the scientific method obsolete. We have big data, we have information on everything, we can build predictive models. We don't need any theories anymore. We don't need to do causal research the way we needed to do it before. Correlation supersedes, it's better than causation. And science can advance even without coherent models, unified theories, or really any mechanistic explanation at all. So two very extreme visions on the importance of prediction, on the importance of causal explanation. And when you get to things that are very extreme, usually there's somewhere in the middle that is the truth, right? Okay, so yeah, they're both fruit. We like both of them, right? So the question is, how do we mix them in a reasonable way? So when I started out working on that crazy idea of explain and predict, I had colleagues, like I was hearing both things and it was not making sense to me and I didn't know the answers myself. And I started working again with Otto Kopius that I mentioned before from Rotterdam. And we started looking at philosophy of science. And it turns out that they had the same kind of debate a long time ago. They don't do any data analysis. So for philosophers of science, they have a different language. And this is very old, 1948, two famous philosophers, Hempel and Oppenheim. They were looking at linguistics, at words, at how you put together logical structures of arguments. And they said explanation and prediction have the same logical structure. And then they have a lot of debates in their journals. And 10 years later, two other people, Helmer and Rescher, come up with a paper and where they say there that it becomes pertinent to investigate the possibilities of predictive procedures, autonomous separately of those for explanation. So after a long debate, they say it's actually not the same. We really have to explore these two things in a different way. It has nothing to do with data. This is just about logic at this point. Debate, 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 debate. 10 years later, in a very famous book called Theory Building by Dubin, he says, the theories of social and human behavior address themselves to two distinct goals of science. One is prediction, and two is understanding. And what's important here is not only saying that they're different, but that they're both important goals of science. So you can't just do one of them and say that you're doing science or advancing science. If you only do one of them, you're kind of stuck in a little place. And that's really interesting because we're going to see soon that the social and management science were stuck in one place, and you're seeing how now things are moving quickly into the other place, but going kind of extreme on the other side. So things are very, very interesting. Okay, so now I want to show you why these things are different. So I said they're different, but I need to convince you that they're different, right? So let's see how they're different. So first of all, these three different paths, they have different goals, and they have different kinds of generalization that they're designed to do. Explanatory models, which are used to test or quantify a causal effect between constructs, right? They're looking at the average unit in the population. So if you think about all the papers that you've read where you have hypothesis, causal hypothesis, right? Our conclusion at the end is about the average household or the average consumer or the average firm or something like that. So an explanatory model is, again, looking at a causal effect between constructs and is focused on the average unit. A descriptive model is a little bit different because there's no causal effect, but we're still looking at the average unit, except that here we're talking about just correlations. And here there's no constructs. So in explanations, we have constructs and theories and causal relationships. When we move to descriptive modeling, there's no more constructs. Statisticians don't deal with constructs. They just deal with variables, right? What we call measurements. And again, focuses on the average unit. So again, statistics 101 that you've taken, they'll always say, oh, a unit increase in price, is associated with a $100,000 increase in something else, right? Holding everything else constant for the average household. All right, and the third one for predictive models, things are really different because there's no constructs, there's no causal stuff, and there's no average observation. Here we want to predict values for each individual new user or unit. So everything changed here. No more constructs, no more causality, and not average. So how can these three lead to the same places? They're all actually trying to generalize to different units, to different things, constructs versus, right, averages. Very, very different. Impossible that you'll get the same model serving all these three different goals. There's kind of a cool analogy to think about how explanation and prediction are really different. So I don't know if any of you have seen the original painting. This is hung up in a museum. It's really beautiful when you see the real painting. It's shocking. But you've probably seen this in lots of places because it's very, very famous, right? It was Van Gogh who painted the original. And think about the story as following. So Van Gogh, I don't know if you know the story, he went a little crazy when he got older, and then they put him in an asylum, like a crazy house, right? And that asylum was across from this little village that you see that he was painting here. So he painted this village while he was in the asylum. So now let's assume that you are a historian and you're trying to learn about this village, and the village is totally gone. There's nothing there today. And all you have is just this painting. So what you really care about, what you really hope is that when Van Gogh was painting this, he was very lucid and not making up stuff and not going very crazy, right? Because you want to make sure, oh, very interesting. So the church was built right next to the houses and the river was flowing there. So you hope that the painting is really as truthful as possible to what the village looked like. Okay, now think of a totally different scenario, where in this scenario, you're a museum that's just got this painting, and you get the painting, but the painting has a really terrible patch right here. Terrible patch. So you give it now to the restoration group in the museum, and they have to repair the patch. So now you're the restorer. You have to restore this painting. As the restorer, do you really care whether the painting reflects the real village, or do you care more about what kind of paints they were using, what were the brush strokes just around that little patch, just around it, right? Just around the patch. Who cares about what's happening on the sides, right? So the restorer cares about something totally different than what you care about if you're a historian. And that's kind of very similar to explaining versus predicting, because in explaining, you really want the data that you have to represent some truth. The model, the statistical model that you build from the data, you want it to represent a truth, the causal theory. You want them to be as close as possible so that you can ask questions about the truth, like the historian wants to ask. But when you're doing prediction, you're more like the restorer. There is no truth. There's just the data, just a painting. All you want is to predict in some areas that are missing. You take data around it, right, and use correlations around it. So it's a very, very different story. That's just some kind of a different analogy to how explaining is different from prediction. Okay, third thing I'll mention is that when we wrote that paper on explaining and predicting, and we submitted for the journal, and the statisticians were reviewing it because it went to statistical science. One of the reviewers came back, and this is how I'm reading this reviewer to you, and they said, I can't read this paper. This paper has no notation. Because statisticians need notation. You don't write long papers like in ISR, MISQ, in a statistics journal. You write, everything's very condensed in notation. And I looked at it and I said, how am I going to put notation on this? How am I going to explain what a construct, how do you do notation? And it took me a long time to figure out. And those comments are the best comments, because when it really hits you, when you have no idea what's going on, that's when there really is something interesting going on. And what I did in the revision was I figured out that the reason I couldn't do notation is because there is no notation for theories and for constructs. There's notation for a regression model and for variables that are measurable, but there is no notation for constructs. So if you look at the final paper, you'll see something interesting. We use a special font. And the font was like a big block font. You see these, we used X and Y in the block font for constructs. But for measures, we just use normal font. For theories, we use this big font, heavy thing, and we use the capital F for like a causal function. But for just a statistical model, it's just F, the normal stuff. Of course, when we did this at the time, I was not familiar with Judea-Pearl's causal diagrams. And in hindsight, of course, we could use do operators. But even in do operators, you only have variables. There's no constructs. So you almost need a whole new language to talk about theories and constructs that we don't have notation for. So that's kind of interesting too. Okay, but I'm not going to do too much with the construct, with the notation here, so don't worry. That paper that I mentioned before, the Leo Breiman Statistical Modeling Two Cultures, he exactly uses this kind of notation. He doesn't have notation for construct. He doesn't talk about constructs because he's distinguishing between machine learning prediction and statistical description. And those both just work in this world. They don't have constructs. So how are things different? Here's another way to think about why they're different. So I showed you the painting. That's a visual way to think about it. Now I'm going to break it down a little more. So let's think about 5 aspects. First of all, theory versus data. When you're doing causal stuff, what's more important, the theory or the data? The theory is super heavy, right? The data is only used there to quantify things and to testing, but the theory is king. You need the data. The data is important, but the theory is really important. When you're doing prediction, totally turns. The data are what matter. If you have theory, okay, maybe. You'll usually use some domain knowledge, but not in a very formal way, the way we'd use it before, right? So theory becomes much less important. Data becomes much more important. In descriptive, same. Data is important. Theory might be somewhat important, but again, it's correlation. It's not about causation. So just the weight of how much these pieces come in are different. Second dimension is causation versus association. So obviously in causal stuff, everything is about causation, right? We're never going to include a variable just because it's correlated with something. Actually, that's dangerous there. We're always afraid of these confounders, right? So causation is super important. Causal arguments, the roles of variables are in terms of causal names and things like that. Whereas when you move to prediction or description, everything is in terms of association and correlation. Nobody talks about causation, no arrows going in any directions. Retrospective and prospective. Usually, not always, but usually, when you're doing causal stuff, it's retrospective. You're looking back. You're saying, okay, I'm going to look at these data and extract from them what is the relationship between these things. But when you're doing prediction, you're building a model that will be used to predict things moving forward. So it's prospective. So you're thinking in a different way. And when you have these different dimensions, it means that, for example, the types of input variables that you put into your model, what we call predictors in prediction or IVs, right, in causal, will be very, very different. For example, when you're predicting, you can only use predictors that are available at the time of prediction. You can't do that. In causal, nobody cares. You can put in whatever, so no problem. Fourth dimension is what's called bias versus variance, and this is a technical term. So machine learners and statisticians, this for them is like the most compelling reason, but it's not the only one. And that is just like with the painting, where you want in causal modeling, you want the painting to reflect the truth as close as possible. That means you're afraid of bias. You want it to be unbiased. You want it to look exactly like the painting. But when you're doing prediction, there's another source that's very problematic, which is variance. And that is whether the measures that you have they have high variance. They can change a lot. That's not so much of a concern in causal models. It's much more of a concern in predictive models. So prediction is worried about both bias and variance. Causal models is mostly afraid about bias. So again, the models, you will be optimizing different things here. In descriptive also, you use both of them. Whenever you're operating just at the level of the data, both of them are important. When the theory is so important, that's when bias takes a major role. And the last one is the one that I mentioned now. This one is actually not in the paper in a very straightforward way. I added this later. That's the focus on an average observation versus an individual unit. And it doesn't have to be like that, but typically causal and descriptive look at the average unit, predictive looks at the individual unit. It doesn't have to be like that. You could be predicting an average unit if you want to, but most studies, that's just the way that things have evolved. Again, that's an opportunity, I think, which is kind of interesting. Nice book by Richard Burke called Statistical Learning from a Regression Perspective. And this is kind of a subfield within statistics that actually does identify a difference between explanation and prediction. What they look at specifically is they look at variable selection. When you have a lot of input variables and you want to select a subset of them, if you're using things like stepwise models, or you're using lasso or shrinkage, if you've taken any kind of classes like this. And they talk about the goal of finding models that are predictively accurate is different from the goal of finding models that are true. So just in this little world, they found that, wow, if we take this smaller subset of predictors, you get better predictions, but maybe now you just lost some very important constructs, right? Very important variables that were supposed to be there from a domain point of view. So that's one of the small areas where you see this very, very clearly. Now I'm going to show you an example in terms of regression models, because regression models, I'm sure everybody has seen, and this kind of will show you how things are very different. So I'm going to use the same, assume that we have the same kind of regression assumption, same model, let's put it that way. And let's say I'm trying to build an explanatory model where X is the IV, Y is the DV, and I think that there's a causal relationship so that construct X causes construct Y. Okay, so I'm going to write this regression model here. And typically what we'll do is we'll measure the Y with some kind of a small, right, with a measurement Y, and then conditional on some measure X. And here's the X, the IV is going to show up very importantly in that model. And the main coefficient that we care about is that beta 1, right? That's what we're going to use to test all the hypotheses. There might also be some other X's in this model, but we just call them controls and we don't treat them very importantly, right? We just put them in there to control for what we really care about. So in this kind of model, We have measures of the X and Y constructs. These are the important pieces. And the beta 1 is the parameter of interest, which we do statistical inference about, right? P-values and everything to test the hypothesis. And what we're afraid about is things like endogeneity, reverse causality, or where we have some left out variables that cause us problems, right? So these are the dangers that we're afraid of. So the controls that we choose here are very carefully chosen just to avoid things like omitted variable bias, backdoor correlations, right? That's the role of the controls here. Now let's think about similar kind of problem, but now for a descriptive approach. So there's no causal thing going on. There's no constructs going on. This is, again, like in statistics, when you learn regression for the first time, this is what it's going to look like. Everything's observable. And you'll notice that here, there is no one X that's more important than the other. Usually put all of them in there and try and figure out which are the important X's that are correlated with a Y. So now things are very, very different. All the X's are chosen because they're somehow related to the Y. What we're afraid of here is that we have multicollinearity. We put in too many things and maybe they're measuring, there's too much overlap between them. So the linear regression will have multicollinearity and we won't be able to test the coefficients properly because the variances will be too big. So how do we choose who remains in here? No theory tells us what remains in here. We could do some kind of statistical significance. We could do variable selection techniques, right? So it's a very different way of setting up the X's, their importance, deciding who stays in and who's out. All the betas are interesting to us. So nobody just looks at one beta. In a descriptive model, you kind of look at all the betas, test all their hypotheses about all of them, and then come up with your conclusions. And finally, you'll see a lot of residual analysis and goodness of fit and test assumptions in statistical textbooks. There's a whole chapter usually on that, because really all these tests of hypotheses are based very, very heavily on normal assumptions and independence and everything that you assume about those epsilons. There's no problem here with reverse causality. Nobody worries about endogeneity. Nobody worries about any of those spurious correlations. It's not a story here. And lastly, prediction. So in prediction, again, everything's observable. There's no constructs at all. Here, what we care about is actually this. We don't care about betas anymore. So now the whole attention shifts to the left-hand side. And what we're caring about is predicting properly for new Ys, right? For new observations, what is it going to be their Y given their measurements X? All these X's now, all these measures are chosen because we think that they correlate somehow with a Y. So that's why we choose all these predictors and dump them into our models, right? And what we're afraid of here is not multicollinearity or endogeneity. We don't care about that. We care about overfitting. We care about fitting a model that's so close to the training data that we have that it won't generalize to new data. And that's why we have this whole issue of data partitioning and having a holdout set, because that's the real worry when you're doing prediction. How do you choose which variables to keep or not? Well, you only care whether when you remove them, do you get better predictions, right? Or the predictions are the same, so you get a simpler model. So that's the reason that you would choose to remove or keep some predictions. And finally, we look at the residuals, not so much for normality and assumptions. There are no assumptions. Nobody cares about this. We just use this to see whether there's overfitting. So we look at the errors from the training and we look at the errors from the holdout. And if we see that the training performance is so much better than the holdout, then we say, uh-oh, this model was probably overfitting the training data. So totally different use of the residuals or the errors that are coming out of the model. Okay, so the point here is that if you get the best explanatory model from the data set, even I give you the same data set and you build 3 different models, they're not going to be the same model. Very, very rare, very impossible, very artificial if you end up with the same model. I'll also mention a few more things about this. So prediction and explanation are different even when you go into practical applications. You'll see that they're different. There was a big competition in 2016 by Netflix, same Netflix that we know today, that was called the Netflix Prize. And they were one of the first websites to build a recommender system that they really cared about, and they wanted to give good recommendations of movies. Because when you're watching movies, you know, it's so annoying when you're finished watching the good movies, you don't know what to watch anymore. Back then, you would get the movies on DVDs by mail. So it wasn't streaming. So you would get a DVD, and if it was not a good movie, oh, it's so annoying. You have to send it back by mail, and then you would get the next one. It would take time. So a recommender system really mattered, and the recommender system was not very good. So people were getting angry, and they decided that they need to improve it. So what they decided to do was to have a big contest. They released a huge amount of data from ratings of their users of different movies. So the data set had millions and millions of rows, and every row had 3 numbers. It had movie ID, user ID, and the rating that this user gave this movie on a 5-star. Millions of these. And a lot of people were competing because the prize was $1 million for whoever can improve this the best. The first thing that most of the people in the competition were doing was they found the movie ID, they mapped it to Netflix website, they found out what was the movie, and then they went to websites like IMDb to find out information about the movie, features of the movie, who were the actors, right? What was the budget, all this information, because they said, oh, that would be great. That will help us predict for new users, like for a movie user, what will be likely the rating. So the goal in this contest was you get a pair, a movie and a user, and you need to predict what will be the rating that this user will give this movie. So that's what most people were doing. Eventually, the winners wrote a paper of they won the $1 million. And here's what they wrote. They wrote, we tried to benefit from an extensive set of attributes describing each of the movies in the data set. Those attributes certainly carry a significant signal and can explain some of the user behavior. However, they could not help at all for improving the predictive accuracy. So that's kind of interesting. They ended up not using any information on the movies at all. Whereas if you were trying to do an explanatory study where you're trying to explain why users rate movies in a certain way, you would definitely need information about the movie. You'd probably also want information about the users. So that's kind of interesting. You get better predictions if you ignore all that information. So that's just a practical example. There are plenty of other examples in elections. Elections, it's very, very clear. You have election polls. So this is from a very nice paper that talks about election polls. And they say there's a subtle but important difference between reflecting current public sentiment and predicting the results of an election. Surveys have focused largely on reflecting the current sentiment, and they're not very good at predicting the outcomes, right? So that's why when people are criticizing, saying, oh, these polls got it all wrong, the polls were not trying to predict what will be the outcome. They're trying to capture the sentiment of what's going right, what's happening right now. So that's another interesting, this is a distinction between prediction and description, right? There's nothing causal around here. Okay, so I'm going to take you through a short ride here of showing you the modeling process that you would go through, very, very generic, if you're trying to do a explanatory versus if you're trying to do predictive, okay? So generally we can break it down into these building blocks. You always start with a goal definition, and then you're going to design and collect the data, design the study, collect the data. Then you're going to prepare the data, all kinds of pre-processing. Then you're going to do some data exploration. You're going to choose which variables you're going to use, which methods make sense. And after you tried a few different things, you're going to compare them, evaluate them, choose your final model, and then kind of use it, right? So that's true for all of these different approaches, but each one of them will make different choices at different parts here. So at the study design and data collection stage, things can be already very different. First of all, you have to decide if you're going to do an experiment or collect observational data. If you're going to do a causal explanatory study, the best thing for you is, if you can, is to run an experiment, right? A randomized experiment. That's the strongest way. It's much stronger than doing observational, right? So you would typically prefer an experiment if you had the option to do it in a decent way. But if you're trying to do a predictive model, an experiment won't necessarily be better, because an experiment, for example, is much farther away from the reality. It's usually less, if it's in a lab, it's totally far. It will be much less rich. You'll have much less variables than you can just scrape or collect or whatever it is. So sometimes a predictive model will prefer more an observational setup where it's much richer and more fine-grained. It's not always the case, but just generally you would think about the advantages and disadvantages of observational data versus experiments in a different way if you're building a predictive model versus if you're building a causal explanatory model. Second question that you might ask yourself is, should I go and collect my own data, primary data, or should I just use some data that someone else already collected? And again, if you're doing an explanatory study, a causal explanatory study, maybe a secondary data is fine, because maybe you're trying to ask a question about this construct and they measured it in some way, and okay, that's fine, I can use that measure that they're using. That's pretty good, that's nice. But if you're trying to build a predictive model and you need to predict, let's say, engagement, how long a person is going to be engaged on the website, then if you have a different data set that didn't measure engagement, then that's something else. It's like how many times the person clicked. That's not good. If you need to predict engagement, clicks doesn't help you. So from an explanatory point of view, you might be able to use the clicks, but for a predictive study, no good. If you need to predict engagement, you need to predict engagement. It's just examples of how you would think totally different about your choices for design. Another choice is, how do I collect the data? For example, if it's a survey, and we know that in causal stuff, we really care about reliability and validity of questions, right? We spend so much time designing the questions well so that they don't have bias in them, and they're reliable. But what if, for example, everybody lies in the survey, but in the same way? So you ask people about their weight, they're always telling you they weigh 5 kilos less than they weigh. In an explanatory case, it's not good because you have bias. There's problem. There's a validity issue, right? But if it's just a predictive thing, no problem, right? You know the future people will also lie in the same way. So no problem. So you think about validity in a different way than you would think about it in a causal case. How much data do you need, right? When we're building these causal models, we care about statistical inference. So you want to make sure your sample is big enough so that you can capture, you have statistical power to test and get a p-value that is small enough for the effect size that you care about. So when you go through IRB, they're going to ask you, why are you collecting this amount of data? And you tell them, oh, I think that this is the effect size that I kind of am going to get, and I need a sample size of this size. But if you're doing prediction, you typically need a lot more data, because you don't care about statistical significance. You want to have enough data so that you can split it into training, into holdout. You want to be able to run all kinds of machine learning approaches that learn from the data. There's no theory, so you have to learn everything from the data. So typically the amount of data and the number of variables that you'll need is probably going to be a lot bigger. So the choice of these choices are again going to be super different. And here's a really cool, interesting thing. How do you sample? So sometimes you have these things called multi-level sampling. We've seen a few examples of these in our class. And there's an interesting paper by these guys, David Afshartus and Jan de Leeuw. I think David Afshartus works at Yahoo now, and Jan de Leeuw is at UCLA. I think that was his PhD. And they talk about nested data. So for example, let's say you want to take a sample of students. So you can go into, you have to choose schools, and then inside the schools, you go into classrooms, and then you take a sample of students. But you can do this in different ways. Let's say you have a budget, you can only sample 1,000 students. You can either choose one school and go in and go into 2 classes and sample everybody like that. Or you could say, let's just take a school here, a school there, and just take a few students here and a few students there, right? You can kind of decide how you want to cluster this. And what they show is very, very interesting. They show that if you want to build a predictive model, then what you care about is really just increasing the group size. So you want fewer schools with big samples, or few classes with many samples. But if you want to build an explanatory model where you can test hypotheses, actually it's better to have many, many, many groups. So even at the level of designing your study, you didn't even collect the data, you would choose a totally different design if you're trying to build a predictive model or explanatory model. That's kind of interesting. Data preprocessing, oh, so annoying, right? You get data and it's always very dirty. One big problem is missing values. We know that in explanatory models or studies, or even descriptive studies, there's a really big statistics field devoted to missing values, where you have to tag them, the missing values, as either missing at random, or missing completely at random, or missing not at random. And then according to that classification, there's different options of what to do to fill them in, to drop them, or things like that. But it turns out that if you're trying to build a predictive model, those guidances are not very helpful. And there's an interesting paper by Meital Sar-Chehansky and Foster Provost that talk about what do you do with missing values when you're building a predictive model. So let's say I'm trying to build a predictive model of something, and I have information on predictors on income and on age and all kinds of things like that. And some people just didn't fill in their income and some people didn't fill in their age, and you have missing values in there. So what do you do? What they suggested is really, really interesting. They said, well, you can build multiple models. In some models, drop the income, don't have income. In some models, don't have their age. And now a new person comes in, and if the new person doesn't tell you their age, you choose a model that doesn't have age. That's a very cool solution, right? And they show how to do it so that you don't have an infinite number of models, kind of a smaller set. But that would never work in a causal explanatory model. You can't just say, oh, let's just drop age out. Age was one of the constructs, right? So you can't just do this. But if it's a predictive model, you would have a totally different kind of consideration. Another thing is the data partitioning, which we always do in predictive modeling. We split the data up into training and test. You don't typically do that in causal modeling. The only reason to split the data in causal modeling, if you have a very, very large sample, is to test robustness. Maybe you try the model here and then you try it again on another piece of data just to see that the model is robust, but you never do it in the way that we do it in predictive modeling, where you build a model on training data and then you evaluate its performance on a whole data set. That's kind of very different. I'm giving you little glimpses of the steps. It's not everything, it's just pieces that make it clear. How do we explore the data? So when we're doing causal stuff, everything is guided by the theory. So you might have something like a DAG at the top, right? That tells you, here are the important variables. Go and look only at these variables. Nobody cares about the other stuff. And there's not free flow exploration of the data. You don't really see any exploratory charts in most of the papers that we're reading that are causal, right? Not so many. You maybe see a descriptive statistics table, but you don't really see charts. They don't give you a lot of stuff beyond the basic statistics. Whereas if you're doing prediction, you really do care a lot about charts and exploring stuff and finding correlations. So that's where you're going to see a lot more exploration in predictive and in descriptive papers. Another exploration thing that people do is things like principal components analysis, right? Or what we saw as factor analysis in causal modeling, where you really care about interpretability of these factors because everything is about causal explanations. PCA is also used very heavily in predictive modeling, but for a totally different reason. It's used for dimension reduction, for reducing the number of predictors, because some machine learning algorithms can't deal very nicely when you have many, 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 many predictors. So you just use the PCA to shrink it down so that you can technically run it and you don't have problems of dimensionality. But nobody cares about their interpretability. So every tool can be used by both, but kind of used in a totally different way. Next step is you have to choose which variables go into your model. So first of all, when we do causal modeling, what determines which variables go in is their causal role, right? We even name them. There's like mediators, moderators. We have special names for them. Whereas in predictive models, they're all called predictors. They're all dumped in the right-hand side if you want. And we just choose them based on associations. The picture that you see here is kind of interesting. There was a guy by the name of Ashenfelter at Princeton, an economist, and he was pretty much of an expert on pricing of wines. And there's economic theory about pricing of wines, like why a certain wine should be priced this way or the other way. And he figured out actually that he can get much better predictions if he just collects some information about weather and humidity and stuff like that. There's like no theory about it. And he just collects that information. And with that information, he figured he can really get much better predictions. Practically very nice, right? All kinds of these wines where they sit in barrels for 30 years. You have no idea how good they're going to be until the person takes it out and tastes it, right? But with his models, just by knowing the temperatures and stuff when the grapes were growing, he figured out that the predictions worked. And he published some of that stuff, and the economists were getting very angry about it. It's hard to find some of these papers. He had a journal. It was closed down, I think. But that was one of the early people in economics that figured out, wait, actually, I can build predictive models by just choosing variables that are based on association, not necessarily causation. You see it in a lot of other there's so many examples where you can just choose things based on association and you don't care about causal role. For example, if you're trying to predict the final prices of auctions on eBay, one approach is take an economist causal model of pricing where it has the number of bidders and it has the original price. There's a whole theory around that. But it turns out that, for example, I cannot, if I'm using data from eBay, I can't plug in the number of bidders because in eBay, if I'm at the beginning of the auction, I don't know how many bidders will be there, right? They drop in. So I can't use the game theory model. There's no way I can use it for a predictive model. That's an example where I can't use ex post information that's not available at the time of prediction. So predictive models need one kind of predictors that are available at the time of prediction. They don't care about endogeneity. They don't care about any of these causal issues. Let me skip. Multicollinearity is a big problem in causal and in descriptive modeling. It's not a problem in predictive modeling. As long as you're not trying to extrapolate to very, very far away areas, multicollinearity is not a problem for predictive modeling. And finally, in causal models, when we include some variables, if we include some IV called A and another IV called B, and we put a moderator in there, we always have to include A and B inside the model as well. Otherwise, we say that it's an unidentifiable model. But in prediction, you can try all of them. And if the prediction gets better when you drop the B out, terrific, throw it out. So also other considerations of keeping predictors or moving them out. After you choose your variables, and clearly by this time, I hope you understand that there's no chance it's the same model anymore, right? The whole study was designed differently. Now you have to choose your methods. Which models are you going to consider? So remember the bias and variance issue that we talked about before. In causal modeling, you really care about bias. So you're going to choose models that reduce bias. We care so much about bias. The word bias is such a bad word in causal modeling, right? Whereas in prediction, we're trying to balance both of them. So we will choose models that trade off bias and variance. For example, if you're even running a regression model, sometimes you will drop some variables and that will maybe introduce bias, but together the bias and variance will get reduced because maybe the variables that you dropped out have a lot of measurement error in them. So from a practical point of view, they have a lot of variance. But when you drop them out, you also introduce bias. When we see these long and short regressions used in causal modeling and omitted variable bias, that's why they're doing it. They're afraid of bias. You will never see causal models using shrinkage models like lassos or ridge regressions because that just introduces bias. You're just dropping stuff that someone carefully carved these IVs and these variables in there and you just let an algorithm pull them out. That makes no sense to someone doing causal modeling, but makes total sense to someone doing predictive modeling. And also the choice of models or machine learning algorithms that you'll use. Definitely you have to use something very, very clear and interpretable when you're doing causal modeling. That's why regression is so popular. That's why we're seeing things like structural equation models where you have diagrams of what's causing what, and you don't see neural nets being run in causal modeling, right? That kind of makes no sense. Whereas in prediction, many times you really don't care about understanding every predictor and how it contributed to what was happening on the other side. Although there is now a big move towards interpretable machine learning, where even if it's not causal and I can't see what's going on, I sometimes want to know which predictors are contributing to predictions, especially in predictions of very important things like in criminal justice, when you're predicting recidivism or when you're predicting life event changes, you're predicting why someone doesn't get a job or like someone doesn't get a loan, like in credit. But that is not causal explanatory. It's predictive that is interpretable, and that's kind of different. So you can still use a neural net, but then find a way to make it interpretable to show why the model is generating this number. Not what were the causes that caused you not to get the loan, but what in the algorithm led to you not getting the loan. And finally, ensembles. Ensembles means that you take multiple models and you combine them together. And that's the biggest trick in prediction. You generate multiple predictive models and you let them all generate predictions, and you take the average, or you let them vote. And that's a huge thing to do in prediction. Things like random forests are based on ensembles and are winners in lots of applications. But in causal explanations, you would never do this. You would never build 5 different models and then put them together. You'd have to choose the one that is closely conveying the truth, right? So you never see ensembles in causal modeling, which is kind of interesting. Okay, so that was building the model. And now we finally get to the step where we have multiple models. We need to evaluate which one's good, which one's not so good, and compare them and select between them. And here we can think about causal modeling. There are 3 components. There's the theoretical model and the theory, which we're trying to validate against the statistical model, right? So we have the theory, we have the statistical model. They're supposed to match. The statistical model, you need some good arguments to why the statistical model matches your theoretical model. And then you also have another layer, which is the data. So you also have to validate the data against the statistical model. So when you see people talking about fit statistics in structural equation models, they're trying to fit the statistical model to the data. But when you're matching the theory to the statistical model, there's nothing to do with data there. There are no metrics there. That's where you have to use your theoretical argumentation on why this regression model operationalizes this theory, why these measures operationalize these constructs, right? So all that part on the left is done by argumentation. Stuff on the right side is where you can use outputs from your model. In prediction, you don't have these 3 layers. You just have 2 layers. You have the statistical or machine learning model on the left, and then you have data. But the data usually we split into training and holdout. So the only validation that goes on here is to make sure that you're not doing overfitting. And that's where we compare the performance of the predictions on the training data to the performance on the holdout data. And if there's a big gap, that's dangerous here. So that's the overfitting analysis. And the other thing we do is we look at how the model performs on the holdout data to get a feel of how this model will work on new data, where we're planning to basically deploy this maybe in the future. So the whole validation and deciding what is a good model is done in totally different ways when we're doing explanatory studies versus predictive studies. Okay, the second point is much shorter. Point 1 was very long. Point 2 is much, much shorter. And that is just saying that how we measure power or performance is totally different. The metrics that we're using are really, really different in all these 3 different approaches. And even if you have very high predictive power, for example, it doesn't mean that the other 2 are high. If you have high explanatory power, it doesn't mean that the other are high. They're different. You just are measuring different dimensions of the performance of the model. So that's why you really have to go and measure all 3 of them if you want to know something about the 3 approaches. So if you're doing causal explanation, then you care about interpretation. You're going to look in the regression at the betas and say, oh, what is the economic meaning, right, of this beta? We're going to look at statistical significance. We're going to look at R-squares, goodness of fit measures. And what you care about most, what you're afraid of, is type 1 and 2 errors. Meaning, oh, we concluded that this beta is significant, that really our hypothesis is supported, but actually it's wrong. Or the hypothesis is not supported and we missed out because we didn't have a big enough sample, for example, right? Those are the kinds of problems that we care about in causal studies. In prediction, none of this is relevant. So in prediction, we care about out of sample performance on the holdout, on the test data. We care about prediction accuracy on individual records. Sometimes costs come in. So sometimes over prediction is more costly than under prediction, or the other way around. So sometimes costs come in when we're doing prediction. We compare the training and holdout performance. And the most dangerous thing in prediction is overfitting. We don't care about type 1 and 2 errors. They don't exist. So overfitting is the danger. So the performance measures and the dangers are so different that you cannot tell me that explanatory power high means predictive power is high. R-square high just means maybe your explanation, you have a strong relationship there. It means nothing about prediction. It can have terrible prediction performance. So you can think of explanation power and prediction power as 2 different dimensions. And you can have theories, very, very good and well-known theories that can be strong in one and very weak on the other. It doesn't make a theory not good, okay? it could still be a very major theory. But for example, if you think about the time when we thought that the sun was revolving around us, right? In the old days, people thought that we were smack in the center of the world and the sun was revolving around us. It turns out they were wrong, right? So in terms of explanatory power, their explanatory power is really, really low. But actually, until recently, when we had GPSs on phones and everything, the way that you would navigate in sea, in the ocean, the ships would be navigating, is they would still be using calculations based on the wrong old theory, where the sun revolves around us. So even though it's the wrong theory, it was still generating approximations that were good enough for navigation at sea, a lot cheaper and simpler to do than basing it on the correct theories that we know today. So you could have theories that are grand theories. We know they're wrong, but predictively, they're actually pretty good. On the other side, we could have other very big theories, right? Like theories of evolution, where we know they're correct. Hopefully, the people who are watching this video will also agree that they are correct. But yet, they're not really useful for prediction, right? We don't know how we're going to evolve in another 1,000 years. There are all these nice pictures with us becoming again like this because of the phones, right? So we can have very grand theories of explanation, but we don't know how they will predict. So there are grand theories that are very strong this way or the other way. And of course, most of the theories in the papers that we're reading and that we are writing are not as grand as these theories. So they'll probably be in some place on this scatter plot, but it's actually very useful to try and plot where the different theories are, where the different papers are, because it gives us a feel of where we are in the field, right? Maybe we're very good on explanation, but we're very weak at prediction. Maybe we're very prediction oriented. So having like a map or a scatter plot of where the different work is, I think is very useful, but I haven't seen that. Okay, so I made until now the two big points. Point number one is that best explanatory model, best predictive model, and best distributed model will never be the same model unless it's a toy example on really artificial data. There's so many considerations that happen on the way from designing the study to at the very end that you'll definitely end up with three totally different models. The point number two is that the performance measures are very different. The reason I separate these from each other is because even when you're doing explanatory modeling, like the causal papers that we see a lot, right, in information systems marketing, you can still evaluate their predictive power. You don't have to do the whole predictive modeling thing. You could still just use the paper the way it was designed to be a causal explanation paper. And you can evaluate, oh, let's see if this theory actually has some predictive power, just by evaluating its predictive power using predictive methods. And that's pretty interesting because that's the first easy step to use prediction for theory building. You can take a theory, it has a model, a causal study, just test its predictive performance. You'll learn a lot about what's happening right there. So I hope you're convinced that they're really different.